You hear the term machine learning thrown around all the time, right? It's in your phone, it's in your car, but what is actually going on under the hood? Well, today, we're pulling out the complete blueprint. We're going to show you exactly how we build a machine that can genuinely learn, think, and make decisions all on its own.
So to really get this, we're going to walk through 4 key steps. First, we'll pin down what learning even means for a computer. Then, we'll check out the different ways they can be taught. After that, we'll open up the tool belt and look at the actual algorithms that do the heavy lifting. And finally, we'll see how we train and test these things to make sure they're actually, smart.
Okay, so let's start with the big one, the most fundamental question of all. When we say a machine learns, what are we actually talking about?
You see, in the old days of programming, a developer had to sit down and write out every single rule by hand. If this happens, do that. Machine learning completely flips that on its head. Instead of giving the computer a mountain of instructions, we give it a mountain of data and a goal. And then it's the machine's job to figure out the rules for itself by finding all the hidden patterns in that data.
Honestly, the best analogy is thinking about how a toddler learns what a cat is. You don't give them a textbook definition, right? You just point and say, "tat," over and over. And eventually, their little brain starts to pick up on the patterns. The pointy ears, the whiskers, the tail. That is exactly how a machine learning model builds its understanding of the world, through examples and experience. Now, for this to work, the model needs to speak a very specific language, the language of data. So let's break down the vocabulary using a simple house price example. An instance, that's just one specific house in our dataset. The features are its measurable details, things like its square footage or how many bedrooms it has. And the target? That's the answer we want the model to learn how to predict, the final sales price. Okay, so we've got our raw materials, all that data. Now, just like building a house, we need to choose our construction method. And in machine learning, there are really 3 main ways we can build a model. And it all comes down to a really central question. Do we give the machine an answer key to study from? Do we just let it loose to explore the data on its own? Or do we teach it through pure trial and error? Let's look at the options. First up is the big one, supervised learning. This is by far the most common approach out there. Here, the model learns from data that already has the correct answers attached. We call this labeled data. It's just like studying with flashcards. The model sees the question on one side, we show it the correct answer, and it slowly learns to connect the dots. But what happens when you don't have all the answers? Well, that's where unsupervised learning shines. For this, the data has no labels at all. We just give the model a massive, messy pile of information, and its only job is to find the hidden structures all by itself. Think of it like finding natural groups of similar customers in your sales data. It's pure, unguided discovery. And last, we have something totally different, reinforcement learning. Here, the model isn't just studying a fixed data set. It's learning by doing things in an environment. It's exactly like training a dog. The model tries an action. If it's a good move, it gets a reward. If it's a bad move, it gets a penalty. And over millions of tries, it learns the best strategy to get the most rewards. This is the magic behind AI that can master video games or control complex robots. All right, so we've picked our learning method. Now it's time to reach into our tool belts and pick the right tool for the job. These algorithms are the specific mathematical engines that actually build the model and make the predictions. So, if you need to predict a specific number, like a price or a temperature, linear regression is your classic starting point. It's all about finding the best-fitting straight line to describe the relationship in your data. But what if your question is a simple yes or no? Things like, is this email spam or will this customer churn? For that, logistic regression is the tool. It's designed to predict the probability of one of 2 outcomes. Now, k-nearest neighbors is awesome because it's so intuitive. To figure out what something is, it just looks at its closest neighbors in the existing data and takes a vote. It's basically the idea that birds of a feather flock together. Simple, but surprisingly powerful. A decision tree basically thinks the way a person does. It just asks a series of simple, cascading yes or no questions. Is the person over 30? Yes. Do they own a home? No. And by following the branches of this flowchart, you arrive at the final prediction.
And for that unsupervised learning we talked about, k-means is a real workhorse. You just tell it how many clusters, or K, you're looking for, and the algorithm goes into your unlabeled data and finds the most logical groupings based on what's similar.
Okay, we have our method, we have our tool, but now comes what is arguably the most critical part of the whole process, quality control.
how do we actually train this thing? And more importantly, how do we know if it's any good?
Well, a model learns by measuring its own mistakes. And that's the whole job of the cost function. It's a piece of math that looks at the model's predictions, compares them to the real answers, and spits out a single score that represents how wrong it was. The entire goal of training is to tweak the model to get that wrongness score as close to zero as possible.
So how do we actually lower that score? The most popular method is called gradient descent. I want you to imagine you're a hiker standing on a mountain in a really thick fog. You want to get to the very bottom of the valley. You can't see it, but you can feel the slope of the ground right under your feet. So what do? You take a small step in the steepest downward direction you can find. Then you do it again and again. Eventually, you'll end up at the bottom. That's exactly what this algorithm does to find the lowest possible error for the model.
Now, this whole training process is a really delicate balancing act. If your model is too complex, it might overfit the data. This is like a student who doesn't learn the concepts, they just memorize the exact answers for the test. It does great on problems it's seen, but fails on anything new. On the flip side, if the model is too simple, it might underfit. It just fails to see the pattern in the first place. The real art is finding that perfect sweet spot right in the middle.
So how do we make sure our model isn't just memorizing? It's simple. We give it a final exam. We never test the model on the same data it learned from. So we split our data up. We use the bigger chunk, say 70%, to train the model. But we keep that other 30%, the test set, locked away. That test set is the surprise quiz. It gives us an honest, unbiased report card on how our model will actually perform out in the real world. And to grade that final exam, we use specific metrics. If we're predicting numbers, we might use something like mean squared error to see how far off our predictions are on average. And if we're predicting categories, we look at things like accuracy, precision, and recall, which give us a much more detailed picture of where our model is succeeding and where it's failing. And that's it. That's the blueprint. From the raw data all the way to a fully trained and tested model. We've covered the what, the how, and the why. So now the final question really isn't about what a machine can do, it's about what you would do. With this blueprint in your hands, what problem would you choose to solve?
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.